Good start. All right, so geometry for dot and cross product. So the dot product, right? When I take a vector u dot v, I get the magnitude of u times the magnitude of v times the cosine of the angle in between them, which is useful because what?
Like the sides of the triangle and the angle by the degrees.
Yeah.
The angle's 90 degrees.
Yeah, when the angle's 90 degrees specifically, right? So
Wouldn't that be the cross product?
when theta is pi over 2, what do you know?
Cosine
Cosine 0, so u dot v is 0. And in fact, the other direction works, right?
Yeah.
So if they're parallel, we'd get 1?
So these two things mean these provide the same information, right? So this really tells me that I use the dot product to test for perpendicular.
Okay.
Cool. It also tells me that, in some sense, the dot product tells you how much two vectors agree, right?
What
Like-
does that look like graphically?
Graphically. What do you mean?
Like, how can you show visually?
Oh, so one
Actually,
thing
a
you might
picture of
consider is if they were unit vectors, right? Like if both these numbers were 1, then when I dot product two vectors, I just get the cosine and the angle between them. That tells me how close they are to parallel.
Oh.
Right? In some reasonable way, this is like almost the percentage by which they agree. Cool? And when you get a cosine, so if I did two vectors that pointed in exactly opposite directions, so if I did minus u dotted with u, what would I get?
No.
-1.
Yeah, if they were unit vectors, I'd get -1, right?
Yeah.
Normally I'll get negative whatever the heck the magnitude of u is squared, right? You guys see that? So, in some sense, right, if I had two unit vectors that pointed in opposite directions and I dot product them, they agree -100%, right? Does that kind of make sense? So that's really a reasonable interpretation. When we do projections later, we'll kind of use that trick. For that cross product, so when I do u cross v, I have to remember there's some geometry here. There's, what, 3 things? So what are the 3 things? So the magnitude of u cross v is something. Maybe I'll write equal. See if we can figure that out in a second. How about the other 2 things?
Oh, those properties?
Yeah, we just used it for something a second ago when we took 2 vectors and we cross product them.
Follows the right hand rule.
Yeah, so there's a right hand rule. And what's the other thing?
Oh, it's a vector.
It's a vector.
No,
That's
is
what?
orthogonal?
Yeah, that's perpendicular to both u and v, right?
Yeah.
That's why this thing only happens in 3 dimensions. Because in 2 dimensions, there aren't any vectors that are perpendicular to just an arbitrary pair, right? And in 4 dimensions, there's 2 sets of vectors.
What about a dot? Like
Dot
just a
products work for
No, I meant in a 2-dimension. What about like a single point? Wouldn't
the
that?
0 vector. Yeah, of course, but that's all you're ever going to get, right? Okay, so what's the other thing here? The magnitude is the
Area of the parallelogram?
area of the parallelogram, which is magnitude of u, magnitude of v, sine of theta, where theta is the angle between them. Right. This guy's the area of, right, here's u, there's v, this thing. Cool. So what does that tell you in particular if u and v are parallel?
Then it's gonna be 0. Sine 0 is gonna be 0.
Yeah. So the result of the cross product is going to be the 0 vector, right? You guys see that? So The dot product's good for testing perpendicular, right? When you get the zero scalar out of the dot product, you know those two vectors were perpendicular. When you get the zero vector out of a cross product, you know those two vectors were parallel. Cool?
Can we get an example of those?
Sure.